All right. Well, good afternoon, everybody. Welcome to the latest IRIS facilitated webinar. This one's going to be on a EarthScope US array topic, EarthScope in Alaska. This is Andy Frassetto broadcasting live from the headquarters office of the Incorporated Research Institutions for Seismology. We're in Washington, D.C. For those of you that aren't familiar, IRIS is a nearly 30-year-old consortium of universities, and it's a science facility funded by NSF to operate programs that enable the earth science community to perform a broad spectrum of geophysical research, mostly in seismology. If you don't know me personally, I'm the project associate. I call myself the Swiss Army knife, who not only sends about 10 emails to you all a week, but also helps to manage the EarthScope US Array program, as well as the Global Seismic Network and some of our other instrumentation and community engagement activities that are headed up by IRIS. So these webinars are designed to highlight the scientific results that are either directly enabled by IRIS or represent important work by some of our partner organizations. The previous webinars are archived on our YouTube channel, which is labeled Iris ENO, Iris ENO, and all of those are also accessible through our website. So I have the website up. You should be able to see my screen right now, and you can use that to browse through past webinars. We're currently working on updating this page so it's a little more sortable. We've had enough webinars at this point that it's quite a bit of scrolling to get to the bottom of things. But this is where this webinar will show up after it's recorded and loaded onto YouTube either later today or Monday. So if you like what you hear today and are interested in some of the other presentations that we've had in the past, or a colleague of yours missed it, there's no reason why they can't go back and find it later. So just so everybody knows, that resource is available. And just to go through how this is going to work for everybody today, only the speaker, Geoff, and I are going to be the voices that you hear. If you have a question as the webinar is unfolding, what I would suggest is you can enter it into the question box that's on your control panel. And so that way, we can go through those at the end. After the webinars are done, I will go through the questions. I will read your name and relay your question to the speaker. I do exercise a very mild editorial authority. If the question's already been asked, I probably won't ask it again. And if the question is kind of unintelligible or beyond the scope, I might ask you to rephrase it or iterate on that. If the webinar implodes, this has happened once before, we can reboot it. What I would ask you to do is it'll take about 2 minutes on my end to sort of reset up the webinar interface, and then just log in through the email like you did the first time. And then both the presentation and the questions are going to be recorded, and that'll be posted on the website, as I stated before. And just for my own personal curiosity, it helps to know if there's groups of you out there watching this. I only, when you sign in, I only see a name on a screen, but I don't see the number of other people in the room who are taking this in. So it's just good for our bookkeeping to know how many people these webinars are reaching. So if there's more than one of you in the room watching this, please let me know. You can just send me a note either via email afterwards, or you can send it to me in the question box. But that does help a lot to know who's out there watching and listening. And last thing, that after the main presentation today, I'll spend about 10 to 15 minutes presenting on some of the work that IRIS and US Array have already done in Alaska related to some test stations and some new methods of emplacing sensors that are going to be leveraged quite a bit when we start deploying seismometers up there in earnest next summer. So I think without further ado, I would like to introduce our speaker today. That's Dr. Geoff Abers, who is a research professor at Columbia University's Lamont-Doherty Earth Observatory, just north of New York City. Geoff received a PhD from MIT, and he was a postdoc and research scientist at Lamont after that. And he's also held faculty positions at the University of Kansas and Boston University. Additionally, he's been quite an engaged member of the IRIS community source governance over the years, which we definitely appreciate. And of particular note, and one of the reasons that he's giving the talk today, Geoff has worked in Alaska for over 20 years, and he recently presented on his expertise in this region at the EarthScope National Meeting. So I think at this point, I will turn it over to Geoff, who will present on seismology and imaging beneath Alaska, EarthScope's final frontier.
Well, so thanks a bunch, Andy, for inviting me to do this, and also thanks for running this great webinar program. This has been a real valuable resource. Um, this is a exciting time for people who've been working in Alaska for a while, such as me, as we're starting to see, for really the first time in a long, long time, a lot of interest and resources being put in. As Andy said, the TA, the transportable array, is coming. This map on your right shows a notional plan. Apologies to Canadians who are lumped into Alaska here. Um, but there's a lot of work done in the 1970s and 1980s early on, and then really, except for a few things I'll talk about today, things have been relatively pretty quiet. The slide on the right left rather shows some of the passive source broadband experiments, the few that have happened in the last decade or so. And so with the advent of EarthScope and programs like GeoPrisms providing a marine complement to it, I think it's very exciting to think about all the things that could happen in really sort of this world-class plate boundary. The main, what's going on here? The main goal of this presentation, sort of thinking about the fact that a lot of people are interested in working up here, is to provide a sort of a broad-based background of both sort of the things that are going on in Alaska, some of the questions and problems that at least I see as having a lot of opportunity, and as well as to highlight some of the major work that's been done. I'll talk briefly about sort of the large-scale tectonics, discuss sort of the earthquake history and some things about seismicity in Alaska, talk about the tectonics and the building of the crust in Alaska and how that applies to our understanding of continents, some imaging work we've done at subduction, spend a couple of slides at the end looking forward in some ways to complement what Andy's going to say about the transportable array. Okay. This is a map showing sort of the big picture here. You can see in the south, the Pacific plate is subducting underneath North America. Big red line shows the trench. These colors and shading show the magnetic anomalies that have been used to infer things like what the age of the crust is and how it formed the incoming plate. And then you can see these pink ovals show the rupture areas of the series of major plate boundary filling earthquakes that occurred in the last century. We'll talk some more about that. And then you can see what's subducting into is underneath the North American plate, both continental and oceanic. But if you go far to the eastern side, although most of the upper plate looks pretty calm, there's been a lot of tectonics, a lot of mountain building proceeding far inland from the active plate boundary itself. So Mount McKinley is this big splotch up here. Big earthquakes like the Denali fault line here indicate a lot of deformation to the north. Some things that are sort of first order about the plate boundary, subduction rates that are shown in millimeters a year by these arrows down here. Now they're on the order of 50, 60, 75 millimeters a year, but the obliquity, the oriented angle between the convergence direction and the trench varies from being almost perfectly arc normal in the Alaska Peninsula, that's the central region here, to increasingly oblique in either direction, particularly as you go west out toward the Aleutian Islands. The obliquity increases until you get to the very far western edge near where you could actually see Russia if you had a house out there. The convergence direction is pretty much parallel to the trench. So although there may be some slab down there, you're not continuing to subduct material. That increase in obliquity sort of balances to first order the increase in convergence rate. So for a large part of the segment, the arc normal convergence is about the same. What's subducting? Although there's a lot of magnetic anomalies, if you look at them, the ages vary over a fairly small range, 45 to 56 million years. Formed, there's obviously differences in fabric. Crust formed at the Pacific Farallon spreading center in the west has a different orientation. In the east, rather, different orientation than Pacific Kula in the west. There's some major fracture zones offsetting these. But the incoming plate, compared to many subduction zones, is relatively homogeneous. The upper plate, though, shows this very pronounced first-order change between an oceanic upper plate in the west, that's the Bering Sea, and a continental upper plate of deforming Alaska here. I should say that it is deforming, so in some respects, this is really not the North American plate. Has often been referred to as the Bering plate, moving a few millimeters a year with respect to the rest of Alaska. But there's a big event about 55 million years ago. A lot of the current tectonics got set when the old subduction zone boundary followed what's now this Bering Shelf edge, leapt outward and captured this piece of the Bering Sea plate, an event that's still probably poorly understood. These parameters and a lot of the other things you might be interested in, I'm just sort of highlighting sort of a global compilation we put together for Alaska and most other major subduction zones are shown in this Syracuse and Abers paper, where we're showing the orientation of subduction, little green arrows showing beneath each volcano, convergence direction, contours of the slab, and then a series of panels showing things like the top on convergence velocity along strike, arc normal convergence velocity. The black dots here show the dip of the plate beneath the volcanic arc, the age of the incoming plate, and the gray dots. And then this panel shows a few different ways of estimating the depth vertically beneath the volcanic arc of the subducting plate. This is a very kind of useful resource for subduction zones in general. One of the things that you can see is that this notion that plates are about 100 kilometers deep underneath all arcs is something that varies quite a bit. And in fact, in the central Aleutians, we see some of the lowest values of this parameter H in the planet. It looks like the subducting, the Wenatchee-Benioff zone is only about 65 kilometers deep beneath the slab here. So this is one of the ways that this is an interesting arc. All of this, of course, generates a lot of earthquakes. This is the most active plate boundary in North America by far. 90-something% of the earthquakes in the United States and 99% of the seismic moment are released in Alaska. Sorry, California. But, you can see in this map the colors are illustrating depth. The main Wenatchee-Benioff zone and subduction zone, deeper earthquakes, of course, farther away from the trench. But you can also see a lot of very clear faults in the upper plate. For instance, this is the aftershock zone of the 2002 magnitude 7.9 Denali fault earthquake. Interesting earthquakes in the plate interior, and then all the way back up to the Arctic coastline. So there's a lot of deformation that's driven by the subduction system here, and because there's sort of been a lot that's known, and also a lot of attempts to evaluate the hazard. I'm just going to take a minute here as a resource to point out that there are several groups that are involved in looking at earthquakes and earthquake hazards in the Alaska Aleutian region. The Alaska Earthquake Information Center is run through the state. The U.S. Geological Survey out of Fairbanks. Alaska Volcano Observatory out of Anchorage has this mission to monitor a lot of the major volcanoes up and down the Aleutians, or all of them. And the Alaska Tsunami Warning Center in Palmer contributes its part to the global tsunami warning process. These, of course, they all interoperate and interconnect. They provide resources like this map here. This is an AEIC USGS product that provides sort of outreach level information about where the major faults and where the earthquakes are, and something about the tectonics of the region as well. The rupture, one of the most interesting things about Alaska is it does have one of the more complete histories of rupture of the megathrust, the big plate boundary fault. And so I want to step in the last century. So I want to sort of take you through that. The first big earthquake in this last sequence is the 1938 Samidi Islands earthquake that ruptured here. It's about 8.2 off of the eastern Alaska Peninsula. And this really initiated this whole sequence of ruptures. The next really big one was 8.6 Andreanof Islands earthquake in 1957 that ruptured much of the eastern and central Aleutians here. Of course, the big one was the 1964 moment magnitude 9.2, 9.3 earthquake. It's termed the Prince William Sound or Good Friday earthquake. This devastated Anchorage, many of the coastal towns in Alaska. What I'm showing here is that both the rupture area and these two patches show the regions of largest moment relief. And this one in particular is one of the largest sort of single asperities that's been observed in an earthquake anywhere on the planet. This still makes it the second largest earthquake, I believe, ever recorded. The sequence then continued. 1965 Rat Islands earthquake, 8.7 was the last really big one in the earthquake series. This fills in almost the entire subduction system, except for a couple of notable gaps. These have been subject to a lot of research attempts to, capture the next big one. Have led to a lot of monitoring, particularly of the Shumagon gap. I think what's been realized more recently as geodetic data has become better. This is probably one of the main creeping sections of a subduction zone that we know about. Is still generating a lot of smaller earthquakes, and smaller, it's sort of magnitude 7s and lower. This is just showing what one sort of filtered catalog of seismicity looks like, and you can see besides a lot of thrust zone earthquakes in the thrust, there's a significant amount of outer rise seismicity, some interesting secondary deformation patches, and again deformation far inland into continental Alaska. Of course, no earthquake record would be complete without pointing out there's also been some observations that suggest non-volcanic tremor and slip episodes occur. This is, I think, one of the first published ones. This is just north of Anchorage. Anchorage is here. The Mount McKinley Denali Fault is up here. This patch is slipped over the course of about 22 months with a moment equivalent about 7.2. And these show some of the early identified tremors that were associated with this. More recently, Justin Brown has used these volcano arrays up and down the Aleutians to show that there's tremor activity in places all over the place in the Aleutians. And this kind of work is just really getting started. So there's a lot of opportunity for understanding these other non-earthquake processes in this very active subduction zone. To show you one example of just how much seismicity there is, I'm going to take you for a minute to one of the experiments that we've done. I'll talk a lot about BEAAR, that's with 2 A's, and MOOS, that's with no E down here. These are symbols just showing where we put seismometers. And I'm going to show you sort of the seismicity that we record in 1 year, the southern MOOS array. Now this MOOS array goes into the region that ruptured in 1964. This green line shows sort of the extent of the aftershock zone there. And so we're sampling really sort of the critical part of the thrust zone. And what we saw was that we were in 13 months locating something over 12,000 earthquakes in this region. This shows, that they nicely increase in depth as you move toward the volcanoes. These triangles here. We're also capturing a lot of earthquakes on the thrust zone. And I'll show you just, one example. This is from a paper that just came out in JGR from Lee et al. Well, first, what this really means, we're recording something between 20 and 40 earthquakes a day, every day. After 13 months, the grads, Lee, I think, starting to pull his hair out, trying to figure out how to deal with all these earthquakes. But it corresponds to, something like 30 some odd earthquakes a day. You can extrapolate or interpolate this to, a few hundred, a couple of magnitude 3s per day, or 600 some odd per year. If we just look at what the seismicity looks like on cross-section, this shows from top to bottom sort of the automated locations, sort of our best attempts are single event locations, and the double difference location here by comparison with sort of the standard catalog that the AEIC collects. And what we can see is that we have an awesomely narrow seismic zone. It's a few kilometers wide from that is virtually flat in the thrust zone in the region that ruptured in 1964, with some pretty clear upper plate deformation patches. We were pretty excited because we thought, here is the thrust zone that ruptured in 1964. When we started looking at the focal mechanisms for all these earthquakes in the upper 50, 60 kilometers, what we realized is that none of them show thrust faulting, and certainly not thrust faulting in the direction that you would expect. So these are our focal mechanisms are beach ball, lower hemisphere beach balls, color-coded by mechanism types. The blue ones are all normal faulting, and green ones are showing strike slip faulting, and so on. What we see in general is only showing on the map earthquakes that are sort of, we think, are in the downgoing plate, so below this line on these cross sections, that by and large these earthquakes are showing T-axes, or indicators of extension down dip. So we interpret these as being all deformation within the downgoing plate, not too far above them. And you can see on cross section toward the bottom here, we see the opposite, mostly strike-slip faulting earthquakes, so with P-axes oriented down the dip of the plate. So the upper plate looks like it's in compression at the same time, lower plate's in an extension. The implication of this is, though, that after 48 years, some odd, we are seeing essentially no thrust faulting earthquakes in the thrust zone that generated the second largest earthquake we ever recorded. This is saying a lot about the mechanics of this thrust zone and sort of how seismic cycles work. There's obviously a lot more room for thinking about this problem, working on this problem, integrating it with geodetic and other sort of observations of how subduction works. Okay, the next part I want to do is talk about what we know about the crust. Probably, a lot of the older, this is showing a collection of most of sort of the imaging, mostly active source now imaging. A lot of this is marine that's gone on in the last few decades. Prior to 1990, the main operation is this thing called TACT, the Trans-Alaska Crustal Transect. It was following the pipeline route and actually went all the way up to the Arctic coast. Really, after the 1980s, other than these broadband arrays that we're talking about here, there's, in 1994, there was one active source expedition that sampled the Bering Shelf and ran a strike and dip lines along the Aleutians. Since then, there's really nothing until about the last 5 years, when the STEEP project offshore here and the Aleut project offshore here, they've both been done in the last couple of years. And so this is really sort of, I think, the beginning of this sort of new era of using modern imaging methods to sample the crust. Just to show you a little bit about what we know, I want to step back and think about kind of what it is that we think about how continents are built and what we worry about. And so this is just, showing a big picture of North America, which is in many ways sort of a type example of how continents form. There are these Archean cores that assembled into this Phanerozoic shield that gradually grew outward through a series of collisions that involved accretion of terranes, of volcanic arcs, magmatism, and so on, both southward, eastward, and also westward as well. Most of the growth westward has been in the last 500 million years, and the main place where this is happening today, and I'll show you in a minute, is actually in Alaska. So Alaska is sort of the modern day analog for a lot of the processes that we think made up North America. One of the things I'm going to touch on is, one of the big problems in understanding how this works is that most of this material that's added to continental crust comes from things like oceanic plateaus and arcs. And there's a real sort of chemical, first order petrologic problem, the andesite problem, and how you get from that material to what we think crust is, that I'll touch on in a few slides. But first I want to start talking about the mechanics of this, and I think a lot of sort of our view of how this happens is colored by this excellent work that CoCorp did, the Continental Reflection Profiling Program in the 70s and 80s, and this is showing really one of the more remarkable lines, this several 100-kilometer long transect across the southern Appalachians, where you can see North America has grown outward by a series of these low-angle thrust faults on which were in place these terranes of increasingly younger, more exotic affinity. We think the same kind of shingling and stacking has gone on to build Alaska, and so I've color-coded here are the major terranes or ensembles of terranes across Alaska. And we'll look at profile. Let's zoom in on this one here. In the north, sort of north of what's now the Denali Fault, the Yukon-Tanana terrane represents sort of Paleozoic material that's displaced somewhat from North America. It basically looks like continental crust. Accreted onto that are these Paleozoic to Mesozoic, mostly arcs and related terranes in the Wrangellia, and then a series of Mesozoic, Eocene, younger arcs, collisional complexes, and so on. The most recent of which is this thing on the bottom called the Yakutat Terrane, which started accreting in the last 5-10 million years, probably based on when we think mountains have started going up, and appears to be still largely accreting now. Geodesy says that it's moving at velocities close to, not exactly with the Pacific plate. So we're looking at a continued collision here, and that's really driving a lot of the modern tectonics that we see in Alaska. We think this line mark T is the old boundary between the Yakutat and Pacific. It's not clear that's active. That seems to have subducted under the Aleutian Trench and extends probably somewhere here. This is the Kenai Peninsula, where is that MOOS and BEAAR array that I showed earlier. I should say I've tried to put citations on these slides as this becomes available, and I'll try to give sometime in the next few days maybe a reference list for all of these. So, we think Alaska is built this way. We'll look at a little bit at some results from the big, 80s vintage Trans-Alaska crustal transect following the pipeline, the main onshore line here with some offshore extensions. This has been summarized recently in a geology paper by Gary Fuis. So this is showing this enormous cross-section from the Aleutian Trench all the way up to the Arctic, 14 kilometers from the Arctic coast. They were sampled, and this is really a series of put together refraction and other kinds of active source lines. And what you can see, if we just look at this upper part, here's the Denali Fault. Everything south of there are these accreted terranes, and you can see the first order is kind of shingling or stacking of terranes. The most recent one is this, this Yakutat Terrane, which is still to some extent going down now, building up modern mountains. So this is really kind of confirms sort of what we think of how the continent grows at crustal levels. Very little is known from this kind of imaging about what happens to these in the mantle. We have a little bit of hint from the broadband arrays that we have looking at receiver functions, and I'll get back to this in some more detail a little bit later, but this is showing this BEAAR project going from, well, you can sort of see from places where these yellow dots are earthquakes, the slab seismicity is 50 kilometers to about 130 kilometers depth, near under the Alaska Range, near Mount McKinley is a little bit along strike. What's colored here are positive or negative conversions in this kind of fancy back projection dipping layer that we have, and I'll take these lines off in a second, but just to show you where we're going, we see strong conversions from the upper plate moho, the top and bottom of the subducting crust, but we also think we see, and I'll back that off here, these in orange, these very low angle detachments within the crust in this receiver function data that suggest dipping terranes. And I should say other group, the Purdue group, has gone and reanalyzed some of this, and I think have sort of elaborated in much more detail on what these terranes look like. So it does look like we can see this kind of crustal structure. There are hints that there are things in the mantle that may or may not be related to the down dip extents. What really happens once one of these things collides to the mantle part of the plates it's subducting, I think is pretty much an unknown at present. The most recent work I think that's been done on this problem has been by the STEEP group. This is their active source offshore work collected the Langset, and I believe 2008. So this is the oceanic part of this Yakutat terrane. This is where the Aleutian Trench sort of splits apart at its end, and so this whole thing here is that Yakutat block that's colliding. What they've done through this active source line is they've characterized what this plate looks like, and remarkably, there's big changes in the thickness of what you might think of as the crystalline basement along strike, but the velocities resemble more than anything else other oceanic plateaus. These sort of continuous, fairly high velocities, the Yakutat, these red lines, and these are some of the better characterized other plateaus. And so the current thinking now is that what's colliding here is a plateau that varies from something like 15 to 30 kilometers thick. If you think about sort of buoyancy arguments that have been made about how thick crust can be before it cannot subduct, this is really spanning that boundary. And so it's sort of been this interesting question of whether it can or cannot subduct. We see hints that at least this thinner western portion actually is subducting to depths of over 100 kilometers. Okay, so back to sort of this crustal growth problem. I'm just going to touch on this because I think there's a lot of opportunity for new work here. But the basic issue is that on average, continental crust looks like what you might call an andesite, a rock with 60% silica, as average P-wave velocities on the order of 6.4, and yet everything that comes out of the mantle in plateaus, in arcs, and volcanoes is ultimately a basalt, is much more mafic. So something is happening between the time that stuff comes out of the mantle and the time that it sort of sits to rest in the continent that is essentially increasing the silica content, changing its composition. And you can sort of see hints of that here. This is a compilation of various laboratory measurements of silica content versus VP. Bulk crust looks something like this, 60 weight%, velocity 7.4. And then this is showing the lower crust in the Aleutians imaged in that one along strike transect that happened in 94. This plot shows VP on the horizontal axis versus depth. The black line shows sort of the continental average from Christian and Mooney. All we can see is that most arcs, and the Aleutians are this red hatchered and solid line region, including that, are faster, certainly at these mid to lower crustal depths, than continents are. That is, arcs don't look like continents, and yet we think continents grow by accretion of these arcs. Some process must be happening that is modifying this stuff in arcs to turn into continents. Because Alaska, again, is this place where accretion is going on now, where arcs are being formed now. There's a lot of opportunity for studying and really advancing our understanding of sort of this basic problem of how continents come into being. There's a lot of approaches. This is showing probably one of the most spectacular active source strike lines. This is showing 1,100 kilometers long strike, not in Alaska, but just south of Japan, and the Izu Bonines showing tremendous variations in thickness and velocity structure of the Izubonin arc at a variety of scales. This is showing at roughly the same scale that one along straight line that's shown in the map view here from sort of the end of the Alaska Peninsula out to the central Aleutians, where we see this variability in velocity, but much less variability apparent in crustal thickness here, and differences in velocity too. So we're trying to understand why this variability is so different. This is, of course, much less well sampled. There are many fewer stations, and you can sort of see by the image that the resolution is less. So there's a lot of opportunities to look here. We have made sort of a little foray into this by taking whatever broadband data we can find that's publicly available from all of these sources that I pointed out earlier that are running stations now, doing very simple receiver function calculations of crustal thickness and VPVS. And this is in a paper that just came out in GQ by Helen Janicevsky et al. We see very low variations in crustal thickness. You're sort of in the mid to upper 30s all the way out. Something funny might be going on right at the end, but we don't see the kind of Izu-Bonin type variability, even though we're going from something that's really a continental arc to something that's very oceanic. There are some hints of an increase in VPVS that might be telling us that bulk composition is changing. But we don't really understand what it is that's regulating crustal composition. And frankly, this is an aliased view. There are not that many control points. Some of these are quite noisy. There's a ton of opportunity to do a lot more, particularly if we can work offshore as well as onshore on these small islands. Okay, so the last part of sort of the science of this talk, I wanted to excuse me, go through some results from the main projects I worked on in the last 10 or 15 years in Alaska. We ran one of the first big broadband experiments. The first big broadband experiment is the BEAAR. This is a broadband experiment across the Alaska Range. Yes, this is a real acronym. Doug Christensen and I ran the station, and the red dots show where we had stations in this array, and we're sampling a couple hundred kilometers across the Alaska Range. Notably, these blue lines show where the seismicity is 50 and 100 kilometers deep. So we're looking for interplay between the subduction system and mountain building. Mount McKinley is right here, the highest point in North America. We then continued this 2007, 2009 for multidisciplinary observations of subduction. Some people call it more observations of subduction. Yellow dots that continue this transect sort of uninterrupted down into, again, this zone that ruptured in the great 1964 earthquake. This gives us about a 450 kilometer long, 500 kilometer long strike section of this. And notably, we're in this region where that Yakutat Terrane, if you remember, that was sort of sitting off here, is subducting under Alaska, and opportunities to see this. I'll say a few words because you've been staring at a screen for a while, listening to science. Let's sort of diverge into sort of the joys of doing field work. There have been two other major Pascal experiments, Xiaodong Song and Christensen, around Arctic, the blue dots up here that went all the way up to the north coast. A main target of this turns out to be the inner core, and looking at earthquakes in the South Sandwich Islands. This turned out to be an ideal place. Those days. And STEEP, which is part of a real big continental dynamics project, had a lot of other elements beyond passive source imaging that's been running for a lot of the last 6 years down here. All of these projects have encountered a few things. Access is really tough. The white lines, and you can't see a lot of them because we use them, are all the roads in the state. Not just the highways, but they're all. Some of these get pretty small. And so one of our main strategies is to make as much use of the road system as we possibly could. There's a very short field season. The snow doesn't thaw down here until sometime in late May, and by October it gets cold and dark. Solar panels don't work very well most of the year because there's no sun, and it's wet and it's cold. And, there's a lot you can want, mosquitoes and predators, and so this is just showing some examples of strategies and issues. This is one of my favorite field vessels that we used to get to remote stations in the Kenai. But you really need to work on things like this to get to some of these remote coastal sites. It is cold and wet. We're having some trouble here. This is in the Alaska Range, trying to figure out where they put the vault last year. And there's two people with very different opinions. One of the problems that is, maybe turns out to be a little bit more of a problem you would like, are large visitors. This is showing one of the smaller sort of Alaska interior juvenile brown bears stalking our car. This is showing the results of probably one of his larger coastal cousins. This is a station, as we approached it after several months in the field, that had been clearly ripped to shreds. There's tooth marks here. There's a battery that was bitten in half, and so on. And this station, it turned out, looked like it ran for about 2 or 3 months after the bear attacked it. It wasn't really until the rain filled up the bucket till the battery shorted out that we started having problems. But these are the sorts of issues that you have to contend with on a nice day, and then of course it's dark. Okay, so just to give you a flavor for what we got out of this is showing, I think, from one of the first imaging papers that we published out of the BEAAR result. This is, we're taking receiver functions, very simple, just a small number of them sort of stacked and back projected toward one source region. What we were struck by right away is that the biggest signals that we see, and it actually turns out some of the largest signals in the horizontal component P-wave train, including the direct P-waves, are mode conversions off the top of the subducting slab. And they're interesting mode conversions. They're showing both these paired negative positive pulses that are very suggestive of low velocity channels. So the yellow circles are showing earthquakes. The diamonds and the black lines show some sort of simple inversions that we did to identify the top and the bottom of a low velocity channel that you would need to produce these receiver functions. And what we find is that there's actually fairly thick crust, 12 to 20 kilometers, subducting down to at least about 130 kilometers deep. All the earthquakes are inside of it. The panel on the right shows a follow-up attempt where we actually did a formal 2D inversion, this work of Stefan Rondonnet, where the colors here show the velocity perturbations that you need in order to produce the scattered wave field that includes the receiver functions. And again, you see this sort of thick subducted crust. This is, I think, a very good candidate for the Yakutat crust that is coming in. These velocities and thickness are very close to what the STEEP people are measuring offshore. There are, of course, some other interesting features. Very stable velocity inversion at about 60 kilometers depth. We're not sure what it is, but it seems to be a robust feature of this back arc, and again, of course, the upper plate. That was sort of what we did from just the BEAAR data and through until about 5 or 6 years ago, and you can see outlined in green sort of then what we think is this subducting Yakutat crust. It's probably the deepest subducting thick crust. I shouldn't say this, but one of the places that is deep subducting thick crust has really been well imaged down to these kinds of depths, down to these sort of beyond where you might expect a volcanic arc. We then, after deploying the MOOS array, then have sort of gone and redone this migration. This is the image that we see from this combined BEAAR MOOS thing. I've turned the map on its side to make it easier to see. This is now a 450-kilometer long section. This is from a paper just submitted by Young-Hee Kim and others, where we're able to see, beautifully the top of the downgoing plate on top of the seismicity through the 1964 rupture zone. These circles are sort of where the tremor is, and then down into this region where we think there's this deep subducted crust under the Alaska Range. It's a good question what it is that we're actually imaging. And in fact, if we start to tear this image apart and look in detail, do waveform modeling, we think the red thing here, so this is the low velocity zone here, is something that at shallow depth is quite different from what we see at depth. At depth, as I showed you before, we're able to model this as a fairly thick low velocity zone with velocities comparable to what we think is a subducting oceanic terrane crust at on the order of 10 to 15 to 20 kilometers thick. The shallow layer, though, seems to be a much thinner layer, 2 or 3 or 4 kilometers thick, that has low velocities, in particular, fairly high Poisson's ratio, VPVS, reminiscent of what's seen in subduction zones elsewhere, in particular Cascadia, where there's a lot of evidence of a couple of kilometer thick, very low velocity channel at the top of the downgoing plate. This may be there because we're subducting a lot of sediments, because there's a lot of fluids at high pressures and high porosity. There's some combinations there, but this probably is the signature in these kinds of data of the thrust zone. So we're able to actually see that here as well. In the cross line, this is, and we've looked at this long line here. We could have enough data to do a sort of weaker migration here, and this is connecting to some of the older refraction data. We're able to see what we think is along strike, this transition from this thick Yakutat Terrane crust to much more normal oceanic thickness of the Pacific crust, somewhere in the middle of this array. So we would say that the edge, the western edge of Yakutat is sort of hitting the coastline somewhere around here. And again, a lot of the microseismicity we see seems to be within the plate, not on the plate boundary. Another thing we've been able to do with this array, looking at the signals, is to do a variety of kinds of tomography. I think one of the more interesting ones has been looking at attenuation tomography. So as signals propagate through hot regions, a lot of energy dissipates. We can quantify that by Q. We do this by looking at spectral fall off of body waves, in particular P and S waves. S waves have been some of the most instructive because that relates directly to laboratory measurements. And what we see are, this is where the downgoing plate, slab surface is somewhere here. What we see are these huge variations in Q and seismic attenuation that are, factors of 20 or 40 between the real hot stuff that's in the flowing part of the mantle wedge and the cold stuff that is in the mantle but closer to the trench, or we call it sort of the cold nose or the cold corner. This has been a real important observation, not just here, but in a lot of subduction zones that we've constantly used these data a lot to sort of argue that this has some big implications for what geodynamic models of subduction zones look like. So here we're showing a pair of two-dimensional models of flow or subducting a plate along this plate interface, and allowing the mantle to flow above it and below it. It's ejecting hot material in and dragging it down along the surface. If we allow this flow to happen all the way up to where the base of the earthquake thrust zone is, 40, 50 kilometers, we predict much higher temperatures in the forearc than we actually observe. So what we've argued here, and we see the same thing in Japan and South America and Central America and so on, is that there must be a zone of coupling extends well below where earthquakes occur, where most of the plate motion still is localized on something like a ductile shear zone at depth on the slab surface. And it's not really until that ends and plate motion then becomes taken up by large-scale mantle flow that we start seeing hot mantle. And these sort of observations in Alaska have been really helpful for calibrating these kinds of models globally. And the last bit from BEAAR MOOS I want to talk about has been interesting and increasingly, I think, controversial story about anisotropy from shear wave splitting. This is showing shear wave splitting SKS measurements taken at the BEAAR network, projected down to a depth of, I think, something like 100 kilometers. And what you can see is that there's a real strong change in very coherent fabric at about where this giant yellow line just got drawn, from things that are oriented down dip in the direction of plate convergence to the south to things, fast directions along strike, changing very abruptly over 10 or 20 kilometers in the back arc. If we look at this in cross section now, so this is going sort of in the obvious cross-sectional direction. This is showing now the black line is the slab surfaces. Yellow area is that area of high attenuation I showed in the last set of slides. These colors then show the azimuth of shear wave splitting. And what we're seeing is as it's changed from blue to red, so this change from slab normal to slab parallel happens very close to where we get into this hot flowing part of the wedge. So we argue in our 2010 paper that what we're seeing is flow in the hot flowing part of the mantle wedge, which is producing this along strike fast fabric, probably a long strike flow at some rate. And this is supported by looking at the actual splitting times. This is the delay times associated with shear wave splitting that increase as you go farther and farther away from the trench, linearly proportional to the amount of path length that's in the mantle wedge. This horizontal axis is the distance that rays spend between the slab surface and the moho of the upper plate. And in fact, you can, from the slope, get a fairly high but not totally unreasonable estimate of about 7 or 8% anisotropy that you need in the wedge to produce this signal. Now, since we published this, a couple of things have happened. One is we've analyzed those Arctic data and those MOOS data. What we find is that that first order change we see in the middle of the BEAAR array persists all the way to the north coast as we see this north, east, southwest fast directions everywhere. And then all the way to the south coast, we see this orthogonal pattern. So this is really, although it looks like it's associated with local subduction, a much larger scale phenomenon. And so we're suspecting we're not just seeing a subduction effect, but there's something more plate scale involved. The other thing that's happened is that there have been a series of papers by Song and Kakatsu that have suggested that a lot of these observations of changes in orientation in fabric globally, but specifically in Alaska, may actually reflect sampling of the subarc mantolithosphere. Now, the fact that we're seeing strong splitting all the way through the MOOS data of the south coast probably has to mean that we're seeing this in this sort of convergence parallel fast direction, something that's coming from below the plate. But there's some other explanations. This is showing absolute plate motion in a couple of different reference frames to point out that this is also parallel to the direction of splitting. We're seeing some large-scale fabric. Other people have also speculated that flow around to the edge of the plate. Margaret Jadamek has written a series of papers about this in Alaska specifically, but globally as well, may play an important role. I think the only solution to this is really going to be looking more broadly at the pattern of anisotropy from shear wave splitting and other signals, not just along the single north-south profile, but throughout Alaska. And that's sort of a sales pitch for looking at TA. Okay, last comment. Andy will tell you what's up with TA. I just want to say, of course, especially as you get farther west into the Aleutians, the amount of land that you have to put seismometers at a grid spacing of 85 kilometers gets to be very little. And probably the only way to address issues having to do with rupture of these big earthquakes, having to do with growth of the island arc, with volcanism, with flow behind the arc, is going to involve putting seismometers in the oceans. There is a model for doing this right now. There's a 4-year series of deployments in an open community access, openly available community experiment in Cascadia. This is just showing a map showing onshore and offshore seismometers that are being deployed or will be deployed or have been as part of this. And so, one thought is to see if something like this, perhaps even with some fraction or all of this equipment, can be moved to Alaska. Of course, this is a challenging and vexing thing. This is showing an enormous 3,000 kilometer long subduction zone. Cascadia fits in. A portion of that is going to take some clever designs of instrumentation to do anything that's at all affordable. But there are tremendous opportunities. Okay, I'm just going to end then by, yes, emphasizing there are big opportunities. We see almost all the earthquakes in the US here. We're seeing the processes by which continents grow probably everywhere active here, as well expressed or better expressed than anywhere else on the planet. There's a spectacular subduction zone that makes volcanoes, that makes mantle flow. We see all of the things that we like to think about at depth. And as well, this is where, because we're seeing subduction impinging on a continent that we've been studying, interactions between flows and processes at subduction and those associated with the big continents. I think I will stop there. Thank you very much.
All right, thanks a lot, Geoff. That was great. I think what we'll do is I will dive in and go for another 10 or 15 minutes about the TA side of the Alaska work for EarthScope. And then, as that's going on, if you have any questions for Geoff, I know I've already gotten several. Keep submitting those, and then while I'm going through this, those will be racked up, and then we will move on and answer questions related to both Geoff's presentation and then the work that Iris is doing currently. So I'm going to switch control back to me. What you're looking at is a uh, Iris DMC map generated from data coming in from all the current TA stations. So this is a snapshot of today for TA network code stations associated with the US Array program. So you can see where most of them are. We just finished occupying the final footprint in the lower 48. There's also reference network and adopted stations spread westward back through the lower 48 US. And then we have a number of stations that were redeployed in 2009, 2010 as part of the Cascadia Initiative. If you swing northward, you can see that there are red dots associated with the TA. And so these are stations that went in primarily last fall, but also there's a test site that's been in there for over 2 years now. And there were two that were just installed this late summer that are part of the wider TA related footprint that has also been installed collaboratively with the Canadian government and the local geological surveys. So just to give you a sense for how this station spacing and availability compares, this is a similar map of real-time seismometers that are currently operating in Alaska. Primarily, these are from the Alaska Volcanic Observatory, as well as the Alaska Earthquake Information Center up in Fairbanks. And so, as you can see, it's not that there's a lack of seismic stations in Alaska. It's just that many of them are distributed in certain parts of the state related to either earthquake or volcanic hazards. And so, really, what the TA as part of EarthScope seeks to do is to sample Alaska in a much more uniform fashion. One of the other points I think is that's important to take away from this map is that if you started clicking on these dots and looking at information related to the stations, not all of them are broadband seismometers. Not all of them are three-component seismometers. So a level of station that will be coming into parts of Alaska that have never had broadband data produced from those areas. So I just wanted to bring those maps up. If you're interested, you can see the URL to these up top. I like the metadata aggregator just as a way to quickly peruse through different data sets that are available through the IRIS DMC. It's very easy to quickly drill down into useful information. Okay, so moving over to the PowerPoint that I made for this, I just want to go through some points related to the test stations that the TA crew has put in already, and how we know that those stations are going to that type of station design and the methods that we're devising are going to bring about a good quality of data for people who are interested in Alaskan EarthScope questions. So I just want to list other people who have worked on these issues with me recently, and really many others. We have TA employees working in Alaska right now. We've been collaborating extensively with some of the other operators in Alaska, including the AEIC. So a lot of neurons have gone into this problem already, and I just want to thank everybody who's already been contributing to this. So I'm going to be showing what are called PSD PDF plots related to noise performance. And so you might wonder what this has to do with Alaska, but this is really the way that we're appraising whether a seismometer is producing quality at a certain grade for research. So this is a plot that was in a paper that came out in about 10 years ago. And what you're doing when you look at this plot is you're basically looking at a histogram from above. And one axis is period, and the other axis is signal power. And so when you see hot colors like yellow or orange or red, you're seeing that the signal at certain periods that's being observed by a seismic station is really occurring within a very narrow range of signal power, so amplitude in a way. So what you're looking at here overall is the black lines are sort of previously established high and low noise models based on performance of globally distributed seismometers. And then the colors that you're seeing are related to the energy that's actually being recorded continuously by the station. And so at the longer periods, you see where surface wave energy might propagate through. You see this prominent arch in the middle of the plot is related to, just in general, higher noise levels related to microseismic energy coming from the oceans. And then at shorter periods, you would see what might be cultural noise. In addition, of course, you have artificial elements to these plots like calibrations, mass recenters, drop packets, and there are occasionally, if there's a big earthquake and you have a small span of time, you would see the signal spectra of a large teleseismic earthquake. Those signals tend to recede if you record more than a few months of these analyses. And so we look at these for the span of months to years to evaluate how a seismic station is performing. And really what we want is this entire power spectral estimate to be as close to this lower black line as possible. Obviously, that's not going to be possible everywhere, but the lower it is and the tighter the spectra is around a certain peak means that your station is probably performing pretty well. So just an introduction, because these plots are going to come up again later in reference to these Alaska stations. Just to give you some context for this, we do these for the TA all the time just to make sure that the TA behaves well. What I'm going to show are plots related to these 5 peaks, which are modes that we're interested in, or frequency ranges that we're interested for the TA. And so what we're going to be plotting on the next slides are the mode, which is the amplitude most observed at a certain frequency over time. So you're going to see one line that either goes up or down based on what period of time, and hopefully doesn't move around very much. So this is a histogram of those mode estimates. And what this is telling you is that for a vertical channel seismometer in the lower 48, the average signal power is about negative 178 dB for 100 seconds. If you look at these other groups of signals, so this is black is 0.1 seconds period, so 10 hertz energy, 1 hertz energy, 6.4 seconds period, and 10.8 seconds period, which are both associated with the microseism. You can see that these seismometers, the data from the entire TA tends to cluster around a fairly narrow range of signal power limits. But what's important to take away from this is that the vertical channel is very quiet at 100 seconds period. If you look at the horizontal channels, that doesn't hold up. The other ones stay fairly the same, but what you're seeing is that the sensitivity of the horizontal channels to long period noise is quite extensive. And so it's changed from negative 178 dB to negative 147 dB. So that's about a 30 decibel shift in terms of the quietness of those channels. So this is really emphasizing the importance of having well-deployed sensors. And negative 147 dB is still, for horizontals, is still really good for a seismometer that's temporarily deployed. But this is a number that we're particularly interested in for Alaska, because that relates to a lot of the work that's done either using surface waves or some other styles of analyses. So we want that number to be as low as possible. This is just a review of how that looks for the lower 48. This is the context that we're operating from when we think about how we're doing work, how we're going to do work in Alaska, as what's been done for the last 10 years for this program. And you can see that this is for the BHN channel for over 100 seconds. And you can see how this performance varies across the array, particularly stations in the mountains where there is less oceanic noise permeating and less cultural noise tend to have better noise performance for this range. So from the standpoint of Alaska, where most of the state is fairly rural, that's a point in our favor. And this also, this one plot, the previous plot, might have allowed you to infer this, but these amounts have changed over time, and you can see that the 100-second period has gotten a little bit louder as we've moved towards both the Atlantic Ocean as well as more larger population centers. Okay, so on to Alaska. This is a plan for the strategy of site emplacement across Alaska as well as the adjacent sections of Canada. So we call this the hub and spoke method. And the philosophy behind hub and spoke is that each hub, which you can see on here is the center of these yellow symbols, the center of those is a airport village that can take in a fixed wing aircraft. So the idea is that there would be a lot of helicopter activity that would be centered at these hubs. And really, given what Geoff presented earlier on the lack of road coverage in the state of Alaska, this is really one of the only ways to get into the more remote areas and impose anywhere near a uniform spacing of stations. So this is the plan for how these seismometers are going to be deployed. The idea would be that a team goes in on a fixed wing aircraft and fills in some, if not all, of the related spoke stations. And so that will allow, as a couple of years from now, as you see station coverage of Alaska filling in during the summer as this work is being done, the hope is that as these stations get put in and certified, that they will be large chunks of the station or the state will light up almost all at once. And so this is just a kind of a briefing level slide of what we hope to achieve in Alaska as part of EarthScope. So again, the blue circles are those existing stations that have some form of real-time data available in Alaska currently. The blue stations, the blue circles, are the idealized grid of TA station coverage. And then the yellow circles are stations that are currently operating as of now. And in fact, there's probably one or two more yellow circles to add to on this map, given the work that was done this summer. So in total, this is going to be around 290 sites. They're going to be spaced at about 85 kilometers apart. They will be inhabited by broadband seismometers. They will have infrasound and pressure sensors on them, just as the current TA footprint stations do. And there may be an opportunity to install MET packages on them, although that is one of these collaborative projects that we hope to leverage as the TA moves in to Alaska and other groups try to leverage that infrastructure. They will have communications. It's not clear how many will have real-time telemetry of broadband 40 sample per second data, and that's because not all of Alaska has cell coverage. So one of the big challenges is making as much of this data available near or real time. And so there may be the opportunity to use either satellite telemetry or Iridium modems. There's currently a trade-off being explored about whether we would use the Iridiums just for one sample per second state of health monitoring and then do occasional data drops where the actual full data stream is obtained. We definitely want to have as much state of health information as possible because as has been very useful in the lower 48 for the TA, we want to make sure that these things are operating all the time. And if there's an issue that needs remediation at the site, we need to know that. The general idea is that this array, somewhat close to the image that's on the screen right now, is going to be deployed fully by the summer of 2017. So how are we going to do this? Just to give a brief overview, a lot of the work that's been done in Alaska already for the TA, as well as parts in the lower 48 that we consider controlled environments like the PASCAL Instrument Center and the Albuquerque Seismic Lab, has been looking at sensor emplacement strategies for either auger holes or coring into rock. And so the tests that have been done have been in placing sensors anywhere from 5 to 10 meters deep using an auger. And so these would be done in areas where you have sedimentation or loose soil. And then the rock coring drill would be used for situations where you actually have an outcrop of basement that you could core into directly at the depth of about a meter to a meter and a half. And so there's been extensive work done by engineering teams from both the TA and groups at the PIC to look at this problem on a very systematic scale. And so the first example of this is a station called Tolk, which is on the north slope of Alaska. And Tolk is sort of the poster child for how we would try to do a lot of these more remote sites. There is a hardware hut that has solar panels, which will generate power in the summer, that encloses some form of power system, either lithium ion batteries that are rechargeable or a fuel cell system. It's not certain what we're going to be doing at every site. There may be some flexibility in terms of power that has not yet been determined, but this is sort of the general concept of what one of these stations will look like. And so Tolk has been operating fairly happily and healthily for over 2 years now, and is using two auger holes, one at 4 meters and one at 5 meters depth, that are about a foot wide, and those are cased in PVC pipe, and they each contain a Geralp CMG 3T seismometer. The philosophy of doing these auger holes to this depth is that it gets below the active layer from permafrost. And so we couldn't do the TA vault at every site in Alaska because we wouldn't have road access anyway. The sort of standard TA vault would probably also have serious issues in areas with permafrost of tilting due to the freeze-thaw cycle on the shoulder seasons. And so this is a way to get your station, get your seismometer below that active layer. And as I'll show at Tolk, it's been quite successful. So this is a noise plot. Again, this is the PSD for the Tolk. The one in the middle is the 5 meter deep hole. The one on the right is the 4 meter deep hole. And I'm showing the BHE on top, BHN, and BHC channels. On the left is a station from that Arctic experiment that Geoff referred to earlier. And what you can see is that for a temporary Pascal style old school deployment, that station actually is pretty good. The vertical channel, as you can see at the bottom here at long periods, is very near the low noise floor, and generally very consistent. If you look over at Tolk, generally both holes fit that profile of that station very well. But where you can see differences is if you look at the horizontal channels, and in particular, if you focus in on, let's say, the BHN horizontal, you can see at long periods that getting down even a few meters deep really reduces the noise signal power at 100 seconds. And so that's a change of about 20 decibels between this temporary station and then the stations at Tolk. If we move ahead, what I'm doing now is just looking at these mode over time or amplitude over time plots for the different frequency ranges. And what you can see at Tolk is that for the BHZ channels, it's around negative 180. And on the BHE channels, you can see a little bit of seasonal variations. There were also, there's a couple outages where there were issues related to the site that were identified and repaired. So lessons learned along the way. But you can see that even with these long period signal changes, possibly due to seasonal noise, that they're still below the 160, negative 160 threshold. So the performance from Tolk was doing very well across its entire deployment. So based on the experiences at Tolk, we wanted to put in a few more stations to test different sensors, different emplacement strategies. So we put in more deployments. One was a cord hole station that used a T120 post hole sensor, and the others used either T120 or STS4B. HDA actually replaced an AEIC so AK network vault, and with a 5 meter deep auger hole. And then TCAL had two that were in place, 10 and 5 meters, and EPYK was the cord hole site in the Yukon. And Poker was a comparison of a standard TA tank, so one like you would see anywhere in the eastern US right now where there's a TA station, and a 5 meter deep PVC cased auger hole. So I'll move on and show some information from those. This is just a picture of the station that's in the HDA station, which is Harding Lake. Again, this was a site that was formerly occupied by the AEIC, but we inherited this as a location to do a test. And what you can see here is that the geology of this site was, I think, very loose glacial loess. And so kind of consistency of baby food when you're digging a hole. And putting the seismometer deeper and getting more insulation and less of an influence from noise either induced by wind in trees or just other cultural noise, as you can see here, has really changed the performance of the long period response. So you're at about 100 seconds here on HDA, and you can see that formerly before it was above the high noise floor. And then when you look at the current performance of the station, again, that 5 meter deep auger hole has really managed to drive down the response beyond about 10 seconds. And so for recording teleseismic body waves and surface wave energy, this is really going to help from the standpoint of doing a lot of the imaging research that we know that the community is interested in doing for Alaska. This is a similar layout for the Eagle Plain Station. If you're interested to see all the work that went into the putting this site in, the crew who did this from the PIC put in a stop action video of this install being done on YouTube. And I think it's kind of a hoot to watch because as somebody who put in seismic stations back in the day, we never thought to record the whole process, but it takes a lot of work, a lot of systematic effort to do one of these sites. And so this video is the story of one of these being put in the ground, and I think it's a really cool thing to watch. So you can go look at that later if you want. And what you can see here is, again, this station was brand new, so we don't have anything to reference it from. But again, you have a very good performance on the vertical channel, and the horizontals are pretty good. They're not quite as good as Tolk was, but we're in a situation here where when the sun is out in the summer, you can get quite a bit of heating on a rock on this outcrop on a clear day. And so although the performance is always pretty good and sometimes extremely good, we can see very long periods being put in by that basement outcrop, possibly tension on the rock due to heating. So it was something that we noticed and we're interested in. But again, most of the data recorded at this station has been extraordinarily good. And so this is just a quick comparison demonstrating the two sites. This is EPYK on the left, and HDA on the right. The top is vertical, the bottom is the east component. And so you can see, again, very good low noise on the 100-second period on both sites. And then you can see maybe some subtle differences between the two, and maybe a little bit of that seasonal shift at EPYK as you get into the summer of 2013 and the sun comes out. But that's still a variation of probably only about 5 decibels, so not too bad. And then the last one I wanted to talk about is the site at Poker. So this is Poker Flats near Fairbanks, and this is looking at, on the left is, I believe, the TA tank, and on the right here is the augered PVC cased hole. And you can see there's an interesting signal here on the horizontals related to the tank. And we think that might be due to either frost wedging or freeze thaw or something seasonally that has really shifted the power over during the duration that this plot was made. On the auger hole, you just don't see that as much. You see a lot more consistency here between both components. And again, it's a nice quiet site by almost any standard. And so this is these are the mode plots. Again, they're both performing fairly well. The Poker one is a little bit better. And then on the BHE channel, again, there's this interesting signal that might be related to some sort of seasonal freeze process that begins and ends quite abruptly. But even at its heyday, it's still a pretty quiet site. So I wanted to segue here, put this reminder so I didn't forget that MOOS at the PIC provided some information related to the tests that they've been doing on more direct burial variations of a Pascal deployment. And so I'm gonna blow this up. And Mouse was nice enough to provide a little description. So I'm just gonna go off of the couple paragraphs that she had provided for me for this one. So Pascal is these are related to Pascal emplacement tests at the same site that we had those TA stations in Poker Flat. They put in 2 trillium post holes and a trillium compact in November 2012, and those are the sites that are over here. Pick 1, 2, and 3. And in July, they went back and reoccupied those stations, reinstalled with dry sand in all those holes. In addition, on the right side here, vaults A and B, they installed Trillium 120 PAs in those to do a more systematic comparison across a wider variety of emplacement styles. And so what we have on the next page is a comparison of what these look like since July. And so these are data that have been analyzed at periods up through 10 seconds. At the long periods, the verticals of all of these shallower post holes are comparable to the deeper TA post hole. And with respect to all channels, the Pascal post holes are quieter than the Pascal style vaults. But I should point out that, again, these are all pretty good performance readings for temporarily deployed stations. If you want to pick out where the TA augured hole is, which is 5 meters deep here, that is actually the vault, I believe, is the orange one that's here, and the auger hole is the light blue one. But again, we're getting very good performance across all of these stations with some variation based on these emplacement styles. And so, it's exciting to see these results. This gives us a lot of confidence that the data that's going to be collected in Alaska is not only going to be good, but as good as anything that was collected with the TA in the lower 48. So I will zap back off of this, and I'm almost done. I think the last thing I wanted to show was basically a summary slide, which was that the performance of these stations that we've looked at in some detail now at these long periods that are sort of the research grade periods related to a lot of the imaging questions has been very good. I think the point that I should make is also that if you look at the higher frequencies, so if you look at the 1 second period, a lot of these stations are also very good, just because there's not as much high frequency noise related to cultural sources in this part of Alaska, or in this part of the continent, I should say, Alaska, the Yukon, and some of the surrounding areas. So it's pretty exciting to see this data, and I would encourage everyone out there who's a seismologist, if you're interested in working with this data, it's all available through the IRIS DMC. I'd be happy to answer any questions one-on-one you have about it. I'll certainly ask any questions that you've submitted today. But I would definitely encourage folks to take a look at it because I think it's great data. So I think at this point, I'm going to unmute Geoff, and I'm going to start going through questions related to his talk, and then we'll wrap things up. So Geoff, stand by. I'm going to unmute you, and then maybe we'll even give you control back. Okay. First question was from Matt Lancaster, and he wanted to know if you could briefly describe how the extents of those rupture areas were determined, the ones that you showed pretty early in the talk.
Sure. By and large, those are based on areas of aftershocks. I mean, these have been around for a long time, so they predate really even having the data to do any kind of fancy finite fault modeling. So pretty much all aftershock areas that people have based on various data sets.
Okay, great. I'm scrolling through the list, and there's another question from Matt that's sort of related. What is the method that was used to determine or calculate the convergence rates?
So the big plate, the Pacific North America rates come out of these global models, like Nouvelle One, that are based on matching magnetic anomalies and fracture zone orientations all around the world and getting closure by various plate circuits. The I didn't show the results, but I sort of mentioned some of these smaller motions, like the Bering's plate motion, the Yakutat plate motion. There's been a tremendous amount of work that's happened in the last 10 or 15 years, mostly using GPS to try to get much finer resolution on the planet's velocity models, and particularly in Alaska. I think Geoff Freimuller and his group up at University of Alaska is sort of the main group who's collected and analyzed some of that data.
Okay, next question is from Peter Heusler, and it's actually more of a comment. Peter says that the consensus is that Yakutat collided by about 25 MA when there was widespread mountain building. I don't know if you want to riff off of that, but that was a note that he added.
Yeah, I mean, there's been some new work that suggests that, and see if I can find the Yakutat. Well, it's what you date and how you get there, of course, are is a random map, but the idea is that a lot of the mountains that are the high mountains that are in this sort of corner have been driven by this Yakutat collision. It's it's a tricky thing to do because it's what of what you're dating is responsible for what when the driver is something offshore. We don't have any direct record of when the Yakutat crust actually impinged on it. We're sort of inferring this based on a variety of, we don't really have a direct estimate of the uplift of the mountains either. So there's a lot of kind of trying to construct arguments of when that should be. But yeah, there have been these older dates have started to appear in the last couple of years as people have looked harder at this problem.
Okay, next question is from Corinne Lamart, or Larmat, and she asks a comment from a total amateur in tectonics. Concerning the andesite problems, I am wondering if the temperature of the mantle could play a role. Cratons were formed a long time ago with a hotter mantle than today. Is there a difference of andesite contents between cratons and young continents?
Now, that's a great question. I mean, I think um, this issue has been known for a couple of decades, and I think one that is one of the ways that people have sort of addressed this is that if you look at the seismic velocity structure of continents, the parts of it that are dominated by these Archean cratons, it may well be that you're looking at a signature of a hotter mantle, a mantle where crust that's subducting is able to melt, and if you start melting oceanic basaltic crust, you might produce something that looks more like a primary andesite. Um, it's not clear though that the younger, by the time you get to the last couple billion years, there haven't been, most models suggest that the temperature hasn't varied that much, and yet it's a real big difference between sort of the 50, 51, 52% silica and the basalt and sort of the 60% that you're seeing for a lot of these bulk crustal estimates. So probably there has to be some other process. A lot of people point to ways of having crust differentiate so that the less dense, more silicic parts are shallower and mafic residue of sort of magmatic differentiation, other differentiation is deep, and then subsequent processes basically cause removal of this lower crust. And this goes under a lot of different names of crustal foundering, delamination, whatever. This has been sort of a controversial process for some time now, but it seems like at least it's an easy way to remove the silica poor parts of the crust and leave you with something that looks more like continents.
Okay, there was a comment from Jim Agnew who about station integrity. It says that he used metal trash cans to hold our seismic equipment on the Susitna Dam project seismic study in the summer of 1980. The bears would knock them over, but they couldn't destroy them. So I guess just FYI.
Yes, you can work really hard on these things. Um, it's amazing what bears can get to and what they can do, though. And we've come to places where we would usually build vaults one summer and then occupy them the next summer. And the idea is that it gives the bears a chance to get used to there being something there. But we've come back to these places where after a summer we find, the 100 and whatever pounds of cement that we had poured in the bottom of the pole pulled out and thrown, 30 yards away in pieces. It's uh, it's clearly something that irritates bears about some seismic faults.
Having worked in Canada and experienced some of these things, I have to agree. It's kind of amazing what they're capable of. So next question is from Jim Agnew again. Do you see any evidence of tearing on the subducted plate in Alaska, especially where it makes that large bend toward the east? And then he says we thought maybe there was a tear in 1980, but the data was not as good then.
Hmm. So the eastern end of the Aleutian Alaska slab, I think, I mean, it still remains, unknown, and there's evidence that suggests that maybe there is a tear and that the intermediate depth seismicity ends very abruptly at about 147, 148 west longitude. But there's other evidence that suggests that, in fact, what might be happening is that the slab just becomes very contorted, becomes aseismic except for little bits and pieces under the wrangles. One of the things that we're actually hoping to do next is to complete sort of imaging of that end of the Alaska slab with more of these dense arrays to look at exactly this question: is what is that slab geometry, and then use that slab geometry to help us better understand and learn more about what these flow fields are that we're inferring from anisotropy. So that's a good question.
Okay, next question is from Eric Kaiser, and he's inquiring in the moose bear profile. The boundary between the thin and thick low velocity layers is also a region of high seismicity. What's your interpretation for that?
Let me see if I can pull up. All right, so here's one of our moose bear lines. Um, this region, I guess he's referring to this sort of region in here where you're making this transition. Um, this roughly corresponds to the down dip edge of, or just down dip of, the megathrust. I'm a little bit, I'm not 100% sure that we're doing this fairly, because I think in this image, the black dots are seismicity we located with Moose, and then the blue dots were a much sparser time, shorter time period that we relocated in Bear. And so some of this transition may just be because we're not using the same catalog, which we probably should do in this figure. Because I think if we start to look at some of these other sections where we have continuous catalogs, and one example I included was, this section. It's not going down the Moose Bear dip, but it's fairly continuously. So we don't see, big increases in seismicity here. We do see this area of relatively low seismicity in the 1964 zone, where all the earthquakes we see are within the downgoing plate. But that's a good question. I'll look more into this. I suspect we're partly seeing an artifact of stitching together two catalogs.
Okay, I have a question from Andrew Goodwillie. It's a little, there's a couple parts of it, so I'm just going to go through the whole thing, and then if we need to go through it again. Could Geoff recap how the North American continent has grown in the east and in the Alaska area? For the eastern margin, it looked like accreted terranes were stacked on top of existing ones, but in the Alaska region, it seems that growth is achieved by terranes being accreted by underthrust processes.
Yeah, so I mean, this map was really about the Precambrian, so everything that's not Precambrian just shows up as blank. Um, yeah, I mean, I think that's a good question. It's pretty clear that, well, it's um, what we see of these images in TACT in Alaska, makes a lot of sense as a sequence of underthrust terranes that have come in. How you look at, I think what he's saying here is the sense of growth, the dip on this is the other way. Maybe someone else could comment about this, but I mean, this is the final picture after not just, this isn't just result of terrain accretion, but the collision of Laurentia with Gondwana. And it's not clear, well, the question, what was actually subducting underneath what here during that collision, I think would be worth sort of piecing together. I mean, it's clear when you get to easternmost Eastern North America, these sort of Gondwana fragments that are there right now. So this may not be showing you sort of the same thing that you think you're comparing it to. Does that make any sense?
Okay, Julie Herrick is wondering if you've seen any results, either in your own research or others, that link tectonic seismicity with a volcanic response in the Cook Inlet region.
Oh gosh, people have looked for these things. I think there are some nice examples, not from the Cook Inlet, but from the Shumagon region that I remember Steve McNutt had looked at years and years ago, where, let me see if I can back up to a bigger map here. So we're talking, in here where there'd be, magnitude 7 point couple earthquakes here, and then clear changes in volcanism in some of the arc volcanoes there. Um, I'm not, in the Cook Inlet region since 1964, there haven't really been any really big earthquakes that would drive that. Um, Somebody else who's more familiar with some of the upper plate tectonics and events might have some more to say about that.
Okay, so there's another question related from, well, this one might be for more for me, from Matt Lancaster, who's asking if there's an opportunity to deploy GPS receivers with the TA. And actually, that's one of the first things that was done as part of EarthScope was putting in GPS stations related to the Plate Boundary Observatory. And so that would be, unfortunately, I don't have a map of that, but there were a considerable number of GPS stations deployed over the last 10 years that look at plate boundary deformation in Alaska that are available from UNAVCO. So I would certainly encourage you, Matt, to take a look at that. And then if you still have any questions, you can get back to me on that, or somebody at UNAVCO, depending on your question.
So
Uh,
if you can, so
oh,
if you
go
can see
ahead,
my,
Jeff.
so I was going to
Oh,
say, yeah,
yeah.
if you can see my screen, yes, I mean, what the geodesy people tell me every time we start to talk about uh, EarthScope moving to Alaska is they say, oh, it's been there for 10 years. And it's true. PBO occupied critical sites throughout Alaska at the onset of EarthScope 10 years ago. And you can see the distribution of the real-time PBO sites as these yellow dots. And some of them are concentrated on volcanoes. Some of them are concentrated in a lot of other tectonically interesting areas. On top of that, there have been a number of campaign GPS surveys that have been done. Um, I'm sure there's opportunity for more.
Yeah, I'm really glad that you put this in your talk, Jeff. This is the figure that I was thinking about, but had no idea where I was going to find it on my computer on short notice. Yeah, and I think it's important to point out that it's great that NAVCO was willing and able to do this so early on, because we've definitely leaned on a lot of their experiences working in Alaska for the last 10 years now. So it's great to have that EarthScope foot in the door up there, because it's going to really help the TA operations when they get ramped up. And in fact, some of the people who are going to be working on the TA in Alaska have already worked on PBO. So it's a good synergy across the EarthScope family. Um, so the last question, before I'll let Jeff go and everybody else go, is on the Bill Harbert is asking about depth versus horizontal noise. Is this being published? And yes, it's going to be published at some point reasonably soon. It's definitely a question of finding the time to write it up, but there'll be an AGU talk on this that I'll be giving in a month in San Francisco. Of course, I don't remember the session right now, but it will highlight some of the lessons that we've learned, not only from the lower 48 TA, but definitely these and placement tests that we've done in Alaska and also at Albuquerque Seismic Lab, among other places. So I can definitely, if you're curious to know more about it, please, Bill, send me a line. Anybody else out there, I'd be happy to tell you what we know so far and share the PowerPoints. But yeah, it's something that we're trying to get formally put out there in the community as soon as possible. I did want to show one more thing before we end. So, Geoff, if you don't mind, I'm going to take control back.
All yours.
Cool, thanks. I realized I didn't, let's see, show my screen. I realized I didn't show this map at the outset in my talk, and it's because I didn't want to degrade it when I put it into PowerPoint. But this is a sort of operations map based on the permitting work that and scouting, well, I should say scouting work that was done this summer by Katrine Hafner, Bob Busby, and some of the other TA folk up in Alaska. And so this was both from the Yukon side on roads and then across central Alaska via helicopter, looking at potential site targets. And so these are the stations where anything that is colored yellow is a TA station grid that is basically satisfied by an existing broadband seismic station. And so, as you can see, that fits well with what I showed earlier, where there was pretty good station coverage in that sort of south central wedge in Alaska. So these are stations that are going to kind of be subsumed into the TA early in its 2014 footprint, and then these magenta or pinkish purplish filled in circles are stations where the recon identified what looked like a good site for a TA station. And so these are the ones that are going to go forward in the permitting process and will be the first clump of stations that are going to be occupied starting in 2014. So the idea for this is that in addition to all these yellow circles, that about 20 TA sites are going to be put in next summer. And then in the following summer, after more permitting work done, and really the crews have cut their teeth on the operations issues and the model for how this is going to be done, that's when the real ramp up is going to be. And so that's when a lot of stations will start being removed from central and eastern US and reinstalled in Alaska. So I would put forward this map as sort of the working plan for what you could expect to see showing up on the TA network data availability, maybe a year from now, a year to 2 years from now is what we're going to have on this map. And then that's going to mushroom from there. So I think at that point, if there's no other questions, which I don't think there are, Geoff, thank you very much. That was a really great overview. And
Oh, you're welcome. Well, thank you for inviting me to do this.
yeah, definitely. I'm really glad you were able to give this overview. And I would say to everyone else out there, thanks for this is kind of a supersized webinar. So I appreciate everybody, more than half, who decided to stick around. That's great. If you want to go back and look through anything related to this talk, please go to the YouTube channel or the Iris webinar page in the next few days, and we'll have it posted up there. And yeah, everybody, thanks again. And I think the next webinar is going to be on the 13th of November and be related to tectonic tremor. So until then, thanks again, Geoff. Everybody, have a great weekend. And for now, sayonara.